Welcome to the deep dive. Today, our mission is taking some pretty complex science academic findings, really, and breaking them down. We want to get to actionable insights about, well, the ocean, one of our most valuable and maybe most fragile resources.
It's definitely crucial. I mean, the ocean's health connects directly to the global economy, to food security. And we're looking at a paper today that really tries to bridge the gap between, say, space scientists and the people actually out on fishing boats.
Exactly. We're digging into a 2011 paper. The title is Remote Sensing and Fisheries, an Introduction. Venetia Stuart was the lead author. And what's key here, I think, is that this isn't just one study. It's more like a summary, a snapshot of this huge international effort.
That's right. That effort was called the Safari Project.
Mhm.
Stands for Societal Applications in Fisheries and Aquaculture Using Remotely Sensed Imagery. It kicked off back in 2007, funded by the Canadian Space Agency, and it had a very clear goal.
Right. It wasn't just about, publishing papers. It was about making the science work. Safari wanted to speed up, like radically accelerate how we use Earth observation data, satellite data, and actually embed it into fisheries research and management globally.
Yeah, embedding it and connecting the space agencies with groups like the Group on Earth Observations, GEO, making it operational.
So where did the material for this specific paper come from then?
It came from a really key meeting, the Safari International Symposium on Remote Sensing and Fisheries. That was held in Kochi, India, back in February 2010. And it was the first big symposium of its kind. Really defined the state of the art at that moment.
Okay, let's unpack that, because a symposium, it sounds academic, but you're saying 157 participants, 30 countries. It feels more like almost an emergency meeting, trying to figure out how to use these orbital tools to manage fish stocks sustainably.
Pretty much. That was the core question. And it's fascinating why satellites are so vital here. Remote sensing, it gives us this unique window into the ocean ecosystem on synoptic scales. Think vast areas, all monitored at once.
Because if you're just on a boat, you only know what's happening right there, right then. But fish distribution, their numbers, where they migrate, that's all driven by environmental factors like temperature, chlorophyll, currents, stuff that changes constantly across whole oceans.
Exactly. Only satellites can really track that kind of change on a global scale.
And India was the right place for this meeting you mentioned.
Oh, absolutely fitting. You had huge contributions from ISRO, the Indian Space Research Organization, and their Ministry of Earth Sciences. India was already a leader in using this tech, especially with their potential fishing zone forecasts, PFZs.
Ah, the PFZs. That's a really practical application, right? Telling fishing boats where the fish are likely to be. But India also provided some key tech, didn't they?
They did. The paper highlights the launch of OceanSat-2 around that time, carrying the Ocean Color Monitor 2 sensor, OCM2. That was a major Indian contribution, especially because, well, as we'll get into, the existing network of ocean color sensors was getting worryingly old.
Okay, so this symposium wasn't just focused on one thing. It covered a massive range. 6 major themes, I think. Can you give us a sense of that scope?
Yeah, it was broad, covered everything from the real practical end, like the harvesting of marine resources, finding fish efficiently, right through to the big picture stuff.
From managing the whole ecosystem.
Exactly. Ecosystem-based fisheries management, making sure efficiency doesn't wreck the resource. Then they looked at specific threats like harmful algal blooms, HABs. Those can be devastating.
Right. And modeling.
Yep. Advanced fisheries models, understanding the long-term impact of climate on fisheries, and then bringing it all back to the coast, the complex issues around managing coastal zones and the fisheries base there. A truly holistic view.
Okay, but here's where, for me, it gets really interesting. Because after highlighting all this amazing tech and potential, the symposium basically sounded an alarm bell. They pointed out some urgent, critical technical problems. It felt like a real reality check.
It was a necessary one. They were blunt about needing serious upgrades. First off, resolution. They needed better spatial and temporal resolution from the satellites. See smaller things, get updates quicker.
And wasn't there something about clouds getting in the way?
Always clouds. That's why they stress needing more microwave-based sensors. Your optical sensors, the ones seeing color like chlorophyll, they're blind under clouds. But microwaves can often punch through.
Ah, okay. So microwaves let you see things like wind patterns, sea surface roughness, even when it's cloudy, things that still affect where fish might be.
Precisely. Crucial data you'd otherwise miss.
But the really scary part was the state of the existing equipment, wasn't it? The paper mentioned the key ocean color sensors, CWIFs, Modus Aqua, Maris.
Yeah, the workhorses, NASA's CWIFs and Modus Aqua, Europe's Maris. The symposium pointed out they were all operating way beyond their planned lifespans, running on borrowed time, essentially.
Wow. Think about that risk. You mentioned these large marine ecosystems, LMEs, worth trillions.
That's the context. The world's 64 LMEs, they estimated, contribute something like US $12.6 trillion a year in goods and services. That includes about 80% of the world's fish catch. And that massive economic engine was relying on hardware that was, well, already technically obsolete over a decade ago.
That's just staggering operational risk. If those old satellites finally gave out before replacements were ready, you'd lose the core data needed to manage this huge global resource.
Exactly. That new Indian sensor, OCM2, wasn't just helpful, it was seen as vital to potentially plug those gaps if the older ones failed.
And even with the best satellites, you still need boots on the ground, or rather sensors in the water, the ground truth issue.
Absolutely fundamental. Remote sensing data is powerful, but you have to back it up, calibrate it, validate it with high-quality in-situ observations, on-site measurements.
But doesn't that just shift the cost burden? I
Yeah.
mean, satellites are expensive, but widespread, high-quality in-situ monitoring isn't cheap either. Who pays for that?
Yeah.
Local groups, fishing communities.
That's the tough governance question, isn't it? But scientifically, you can't skip it. Without measuring things like bio-optical properties directly in the water,
Yeah.
your satellite models, well, you don't really know how accurate they are or where the errors might be creeping in. It anchors the data.
And that job gets even harder near the coast, right? They talk
Yeah.
about case 2 waters.
Right. Case 2 waters. Think optically complex coastal areas, estuaries, even some inland lakes. The problem is the satellite's trying to measure chlorophyll, the phytoplankton greenness, which indicates potential fish food. But in these waters, you get interference from, well, everything else.
Like river runoff, sediment.
Exactly. Color dissolved organic matter, suspended sediment. It turns the water into a kind of green soup. The satellite sees green, but it struggles to tell if it's useful phytoplankton green or just, muck.
So the standard algorithms they use for the open ocean just fall apart.
Pretty much. That's why they highlighted the need for really refined, site-specific algorithms for these coastal zones to make the satellite data actually useful for managing those local fisheries.
Okay, let's pivot to the successes then. The so what? Where has this tech actually made a difference? India's PFZs seem like the poster child.
They really are a standout example, translating complex satellite data temperature, chlorophyll, into these potential fishing zone forecasts. They use ICT, information and communication tech, to get these advisories out to the fishing fleets.
So the boats know where to head. What's the benefit?
Huge benefits. Better harvesting efficiency, less time spent searching empty water. That means significantly less fuel used, which saves money and cuts emissions. And of course, big socioeconomic pluses for the fishing communities.
But there was a big warning label attached, wasn't there? Efficiency is great, but not if it leads to wiping out the fish.
Absolutely critical point. The symposium was adamant. Using remote sensing for PFZs must go hand in hand with solid ecosystem-based management. The forecast helps you find the fish. The management plan ensures you don't take too many. Technology enables sustainability. It doesn't guarantee it.
And making those forecasts even better means pulling in more data streams, not just temperature or chlorophyll alone.
Right. It's about synergy. Combining chlorophyll, sea surface temperature, SST, even sea surface height anomalies, SSH, from altimeters, looking for where different features like fronts or eddies converge. That's often where fish gather. It's about mapping the productive hotspots.
You mentioned the $12.6 trillion value of the LMEs earlier. The paper sounded a pretty serious alarm connected to that value, didn't it?
It did. It flagged findings suggesting that primary production, the very base of the marine food web, the phytoplankton, was actually declining in some large ocean areas, likely due to climate variability and change.
Wow. So less food at the bottom means.
Inevitably, less fish higher up. That's a massive potential hit to that multi-trillion-dollar economy and global food supply. A stark warning.
But they also highlighted solutions already working, like Turtle Watch in the Pacific. That sounded fascinating for reducing bycatch.
A really powerful example. They use data from electronic tags on sea turtles to figure out their preferred temperature ranges. Then they overlaid that with satellite SST data.
So fishermen could see, okay, this temperature zone is where turtles are likely to be, and just avoid it.
It gives fishing fleets near real-time maps of likely turtle hotspots based on temperature, allowing them to fish elsewhere and dramatically cut down on accidentally catching turtles. The symposium strongly recommended looking at adapting this model elsewhere for other vulnerable species.
And they even link satellite data to the health of fish stocks themselves, the shrimp study.
Yeah, that was on the eastern Scotian shelf with northern shrimp, Panellus borealis. They successfully correlated remotely sensed environmental data with the growth and, importantly, the recruitment, how many young shrimp survive for that stock. It showed you could potentially use satellite data as an indicator for stock health, a new angle for ecosystem
And
management.
then there are these big integrated systems, like Teredas in Japan.
Right, Teredas. Traceable and Operational Resource and Environment Data Acquisition System, used for squid and skipjack tuna. What was key there was combining the PFZ forecasts with vessel monitoring systems, VMS.
So you forecast where the fish might be, and you also track where the boats actually are.
Precisely. It creates a feedback loop. Forecast, fish, monitor, a much more complete management picture.
Okay, so if the tech works, and we have these success stories, the path forward seems clear. Get the data out there. Accessibility sounds like the big theme for the future.
Absolutely. This is where it shifts from a purely technical challenge to, well, a political and logistical one. The loudest call was for open access, a move towards global time series databases for all the key data, SST, chlorophyll, the crucial in situ stuff, and reliable catch numbers, too.
And accessible quickly and cheaply.
The recommendation was explicit. Near real-time data available at low cost or ideally no cost. The science is there, but getting different countries, different agencies to actually pool their data openly, that's the hurdle.
The classic sharing nicely problem.
You could say that. But beyond just access, they also pointed to some newer techniques that needed more work, more validation.
Like that composite frontal map thing, what was that again?
Ah, yes. It's basically a way to simplify things. Instead of looking at day after day of shifting temperature and chlorophyll fronts, you combine them into one composite map over, say, a week. It helps highlight the persistent features like eddies or strong fronts, making it easier to see patterns relevant for species distribution, or maybe figuring out the best boundaries for marine protected areas.
Makes sense. And getting better at predicting harmful algal blooms, too. Needing to know which bloom it is.
Exactly. Refining those early warning systems. Moving towards species-specific detection if possible. Knowing if there's a bloom is one thing. Knowing if it's a toxic species is critical. Plus, refining probabilistic models like Bayesian networks to estimate primary production and fish potential. Lots of refinement needed.
But all this amazing science is useless if it doesn't reach the people on the water, right?
Critically important point. They stressed the need to socialize the science, training, education for fishing communities, making sure they understand the benefits and how to use the information for sustainable fishing. It has to translate into practice.
And the really long view climate change monitoring, using satellites for disaster response like tsunamis, it covers the whole spectrum from daily fishing ops to global threats.
It really does. So what's the takeaway? I think the big message from Kochi from this paper is that the tech exists or is within reach to manage our oceans much more sustainably. We're talking about that $12.6 trillion LME economy, but actually doing it depends on overcoming these political and technical barriers to get truly unified, open access global observation systems. They strongly urged repeating this symposium because the stakes were only getting higher.
Which leaves us with a pretty sharp question, circling back to those aging satellites.
Yeah.
If the whole system, this multi-trillion-dollar management effort, relies on continuous data, and the core satellites were already past their use-by date over 10 years ago, what's the plan now? What concrete steps, political will, funding are actually in place to guarantee that data stream doesn't just stop?
Yeah.
Because if it breaks, the fallout for fisheries, for the economy, it's almost unthinkable.
That remains the crucial governance challenge, doesn't it? Ensuring that continuity.
Thank you for joining us for this deep dive.